Hi, in this video I'm going to show how to use the MATLAB Computer Vision toolbox within Simulink. The example that I'm going to show count vehicles that are driving through a street. The way that this is done in this case is using optical flow to facilitate the segmentation of the images and then apply a threshold that is dynamically determined, and with that we feed the blob analysis to get the bounding boxes of each car, which use to count the cars. The model that I'm going to show is going to use a computer vision toolbox blocks that are packaged in mask blocks, and within the mask they are invoking S functions, and S functions is a mechanism that Simulink provides to integrate external C++ code into the Simulink model for both simulation and code generation. And at the end of this video, I'm going to generate code for the model, and you will see how this S function code is integrated gracefully into the main step function of the model. That is one way of integrating computer vision code from the toolbox into Simulink. Another way is doing a MATLAB function block. And there are examples of MATLAB function blocks in this model that I'm going to show in the video, but not invoking the computer vision toolbox. If you want to see how to invoke an example of integrating the computer vision toolbox through the MATLAB commands, see the reference in this video in which there's an example that implements the SLAM algorithm for UAVs, and it does it in a Simulink model that is using a MATLAB function block that has all the MATLAB code and the computer vision code to implement the SLAM algorithm. Okay, so I'm going to start giving a very brief description, very brief overview of how the model works. Then I'm going to enter in more details of the behavior of the model, and I'm going to use some debugging techniques to show how those debugging techniques in Simulink can facilitate the understanding of a model. And finally, at the end of the video, I'm going to generate C++ code for it. Okay, to start, we can hit the open example of this article, which is in the references of the description in this video, below the video, or alternatively you can put the name of the model, which I'm going to also put in the descriptions. And yeah, this is the model, and you can see that the main parts are the video, which is coming from this video reader, a multimedia file block. And you put just the name of the file, and we're going to convert it from RGB to gray, take away the colors, just have the intensity. Then we use the optical flow. From the optical flow we apply the segmentation, and the blob analysis happens inside of here, and then we get the bounding boxes and then display the results in different video viewers. Okay, and in here we have a dynamic threshold that is basically taking the spatial average and the temporal average to create the threshold for the vectors, the magnitude of the vectors coming from the optical flow. We apply a median filter to remove the noise. We close it to get more solid blobs, and that is passed into here. We use this MATLAB function block to remove the upper part of the image. We then apply the blob analysis to get the bounding boxes, and then we have some offset because of the top segment that was removed. And finally we feed those bounding boxes to here. We can also control the speed of the model. So let's run it. And one good thing about this model, this is a good detail for the example, is put the stop time into infinity. And that is great because it doesn't put the person that is reading this model in a rush to quickly understand, because it's gonna look forever, and that helps. Okay, so let's see at the video. So I just hit the simulation button up here, and you can also pause it and stop it if you want to understand what is happening. And yeah, I'm gonna move the videos in here. Okay, so here's the original video. You have a bunch of cars passing by, and this is the optical flow. You can see it's kind of hard to see like this, but I'm gonna put it slower in a moment. And you can see that you have the threshold. This is a threshold image coming out of here, and this is the image coming out of here with the visualization of the vectors. You can see that this optical flow is being passed to the display block, And as I mentioned before, the detection happens below this line. There's a MATLAB function block that is getting rid of this. And also this is the number of cars that is being counted. Okay, so I'm gonna put this a little bit slower. Okay, I just flipped the switch down here, but I didn't have to stop the simulation to do that. And you can see that the optical flow is gonna detect vectors with intensity and magnitude for the pixels that are moving. For the pixels of the background of the street, basically they're not moving, so the magnitude is 0, so we don't see vectors for them. And those vectors are going to facilitate us to basically find these objects in the binary image. Okay, now I'm going to go in more details of understanding the model. I'm going to stop it, and there are three techniques that I'm going to show of how to understand the model. One of them is to look at the values in the signals while the simulation is paused and running, but paused. And I'm going to put video viewers in the different stages of the pipeline of the model to see how the images are being transformed block by block for those that apply. And also I'm going to debug through a MATLAB function block in addition to that. But one important thing before starting all of that is seeing the types. When debugging either MATLAB or Simulink or any language, it's important to know the types of the variable because they give you a lot of information on the spot. So let's go to information overlays and let's put the base types and signal dimensions and base types. And this is going to compile, and we can see that this is a color image. The third dimension is the red, green, blue. And once you change it to gray, you lose the third dimension. And in here you see that the spatial dimensions between the outside of in the output of optical flow are the same spatial dimensions as the input, but the only difference is the base type. The base type is single here, but it's single complex in here. And it is complex because a complex number has real and imaginary, and the real and imaginary can represent the x and y, which are the vectors of the optical flow that we see in here. You can see those vectors, so that's why we need those complex numbers in there, but we cannot display it. So if you put a video viewer in here, you're gonna see the original image that we see in here. And if you put a video viewer in here, you're gonna see a black and white black and white image. So I'm not gonna do it here. I'm gonna do it inside of here. I'm gonna put the video viewers in here. Okay, so we cannot display the complex image, but we can display the magnitude. So we take the magnitude of the vector of the complex, and now we have an intensity, and that corresponds to the velocity. And that velocity we're going to use, as mentioned before, to filter if you have high enough velocity, it means that you're moving. So we're taking the mean, you can see the types, that this is a special type, a matrix, and this is a scalar. So you take the average across all the pixels in the image. And here this is an S function. It's a mask, Control U. You can see under a mask by either using Control U, or you can select from here a mask, look under mask, and you can see that it's an S function. So this is gonna basically has like a local state that is collecting the average across each step in the simulation. So you get a spatial and temporal average, and that is compared against all intensities. And if you are above the average, both the spatial and temporal average, then you're gonna get a 1. So let's take a look at how it looks. Let's take a video viewer. I like having a very concise name to be able to have multiple of them without cluttering the model. Okay, so this is the input, and let's see how it looks after thresholding. And then we have the median filter, which is just another S function applying the median filter. And again, I could have a MATLAB function block in here calling the median filter function from MATLAB. That's another alternative of using computer vision. So let's see what the median filter does for us. And finally, let's see what close is doing for us. Inside of here, what is going to happen is I'm going to put also video viewers down there in a moment, but let's take a look at this first. Okay, there they are. Okay, we have the form that we just created now. Okay, it's going to take some time, so I'm going to pause. Okay, so we have it, and we can see the intensity in here, and it looks like there's almost no pixels, but the intensity does not show up because it's too low. But if you put it in the threshold where the output is 0 or 1 because it's a boolean, then you can see that there were more pixels, there were more intensities that we could not see in the original image. So there were plenty of vectors, and of course the value of the intensity of the background is 0, so it's not going to make it into this binary image. And we may have some noise in here, so that when we apply the median filter, that noise, you can see that there was some noise in here, like this. When you see that noise in here, it doesn't appear in here, and that's because of the median filter. That basically median filter is a stencil operation that takes the average across the neighbors, and by taking the average, you can remove a small noise, and you can see this is more clean. And then we apply the close. You can see that the shapes are a little bit with holes, and by applying close, we have less holes in our blob, so we have a more solid blob in here, and that is important to determine the things like centroid and the bounding boxes of the blob, and that is what we pass to the blob analysis. So let's take a look at what happened in this submatrix first. I'm gonna pause. First, I'm gonna stop the simulation and just avoid the clutter. Just get rid of all of them, and then I'm gonna do the same in here. Okay, I added a video for the input, and it's the binary image that we already saw. And what happens after this MATLAB function, you can see that it's the same image, but we are cutting away from line 22 until this line. And how do we know that? Let's put a breakpoint inside of here to see how this is cut. If we put a breakpoint here, it's gonna take a while until it hits it, so I'm gonna pause until I get the hit. Okay, I got the hit, and you can see the dimensions of the image is 120 by 160, and when we're doing it, we have this parameter in the block, and I'm gonna show you where that parameter is. If you hit Ctrl H on the model, you're gonna go to the Model Explorer, and on the Model Explorer you get to the model workspace, and you can see a line row is a parameter, and that parameter is passed as a parameter in here. It's not in here, but if you go down here and you go to modeling, there's a function to edit. When the model is stopped, you can actually edit. Let me pause this for a moment. Yeah, stop the simulation. So if you go to ports and data manager, you're gonna see the API of the function of the MATLAB function block, and you can see that this is a parameter and it's taking the value from the model workspace. So it's kind of good to understand where things are coming. So this is and it's declared as an input, but it's really a parameter. The only I/O, as you can see here, the only input outputs are U and Y, but this is a parameter. So although you see it as a parameter in here, when you go here, you only have one input, the U and Y. Yeah, so that's where it comes from. So okay, let's gonna run it again and hit the breakpoint. Okay, so we have that is 22 as we saw in the model workspace. So what it's gonna do is gonna take for the rows starting on 22, it's gonna go until the last one. The first element of this array is 120, so it's gonna go from 22 to 120. So it's gonna cut out the first 20 rows, and that's why we see That's why we see that the image is cut in here. We see, but what happens after that? We feed it to to the blob analysis, so we're gonna get the bounding boxes. So notice that we don't use a video viewer after this, because now we don't have an image, we have bounding boxes. This 4 represents x, y, width, and height. And notice how this line is different from this one. This is a variable size signal, so the maximum is 80, but it doesn't mean that you're gonna have 80 rows. You can have 1, you can have 0, you can have 2. In here, you always have a 99 by 160. It's a fixed static matrix. This is a variable size matrix. Okay, so what's gonna happen? This is gonna give us xy coordinates that are relative to this box right here, which is the one that we're filling here. But then we have to add to the y 22. So that's the reason why we have this array vector add. So let's put a breakpoint here. And so we're gonna hit the breakpoint eventually. Let's stop it and run it again to see if we can hit it. Okay, so we hit it. Let me see how many dimensions we have. We have 0. That's not an interesting scenario. I would like to see when the first dimension has a value of higher than 1, so that we get a couple of rows. If you take a look at the U, it's gonna be empty. It's gonna be just 0. Doesn't even show anything. So let's put a smarter breakpoint. You can do right click on the breakpoint and set modify condition and set that I want to stop when this is higher than 1. Okay, so let's stop the simulation and run it again, and now we're gonna get a more interesting scenario. Okay, so I'm gonna pause until that scenario appears. One thing that I forgot is that I put the simulation in slow motion, so by making it faster, it's gonna get it faster. Okay, so what it's gonna do is it's gonna take the first dimension, which is 2, and it's gonna apply red math. This is gonna be 2 and 1, so it's gonna repeat these 2 in the row dimension. So after this, we're gonna have 2 rows of 22 and the rest are zeros. And that matrix is added to these bounding boxes. You can see a bounding boxes, so it's gonna add the 22 in here and 22 in here. Only this, the other ones are gonna remain the same. And you can see it in here, the output value of y now it has 22 extra than this one. And the reason for that is because we want to do the bounding boxes relative to the original image, not to the cut image that we did. Okay, so let's get rid of this clear breakpoint and let's continue. So now that we have the bounding boxes, we are gonna display them. We fit that bounding boxes, the threshold image, and we provide also the optical flow image and the original image to this to display it. There's this function in here. We have a MATLAB function block that is gonna get the vectors in a way to display them. This is the MATLAB function block, and I'm not gonna go into details, but what it's gonna do is compute the vector lines. And then those vector lines are going to be fed into these draw lines, which is another S function that is passed to the video viewer, and it's going to display the optical flow lines. Okay, so the bounding boxes are going to be fed into this block before going here, where we display the bounding box. And notice, in addition to the bounding box, we also have this white line. We have this black box and the count number of cards. Okay, so there's a little trick in here. As I mentioned before, this is a dynamic dimension. It says 80 by 40, but doesn't have to be. And if we put here, we can see the value. You can see the dimension, the actual dimensions. But it is moving, actually. If we want, let's pause it for a little bit. And we can see that now we have 1 by 4. So we take the dimension property using the probe block. This is a pure Simulink block, and we take the signal dimensions and with that we get the 1 by 2 because we only have 2 dimensions, and that's going to get the 80 and 4. And then we select or we pick up the first element, which is the first dimension, which is 80. So we get a value of 80 here. You can see, we get a value of 1, not 80, because it's a variable size dimension. So we only have one bounding box. So we're getting the first value of the dimension. So this is important because we only know at runtime what the value of this first dimension, variable dimension, is going to be. So that the number of bounding boxes is basically the number of cars that we found, and that is basically converted to the signing type and passed into this another S function to basically put that as a text in the image. So we have the image here, and we put it into here, and that's why we see the number 1. But notice that it's behind, in front of a black box. So that black box, it comes from this assignment block. So we have a 0 for black, and we take the image and we select the top upper left, the first 30 pixels, 30 by 15, and that's the size of the bounding box that we see here. But also we have the white line, and for that we only select a range in only one dimension, and then we put 1 because it's white, and that's the line that we see here. And the rectangles, the bounding boxes, are coming into this, which is another S function, and basically put the bounding box. Okay, so that's all for the video, and this is just basically displaying the threshold image. So that's all for the video. For the understanding the model, I'm gonna generate code as I promised at the beginning of the video. I'm gonna generate code for this. I'm gonna stop the simulation, and if you want to generate code, you can go to the apps, go to embedded coder. You can find it in here, embedded coder, and you can hit the build button. You can hit the build button in here, but I prefer doing it like this. You can do RTW build. You can use the name of the model like this. You can do this, but also you can use BD root, which is the name of the active model. In this case, the same that I typed in there. And I'm gonna just do RTW build to generate code. It's gonna take a while, and in the first try, it's gonna error because this model is not ready for code generation. It is using variable size signal, and as you can see here, it's gonna complain saying, okay, to enable variable size signal, open configuration parameters and box and select variable size signals. And you can hit the fix button here, and if you hit fix, it's gonna fix the issue, and then you can generate code again. But I'm gonna show where that happens. To see the configuration, you go to settings, go to here, or you hit Ctrl E, and you're gonna get to the same place. And you can search for variable support, variable size signals, and there you have it. It is on their interface. You just have to check it here and hit apply. But look what's gonna happen if I hit fix it. If I hit fix, then now it's checked and applied. So that's all I have to do, really. I don't have to go up there. Okay, so I'm gonna start over again, and it's gonna take some time, so I'm gonna pause. Okay, code generation is complete. It took less than a minute, 38 seconds, and you can expect the generate code in here. The name of the model is this is basically the entry point. You have around almost 3,000 lines, and you can see that in 15 minutes or 10 minutes I was able to go through explaining the behavior of this model through Simulink, because it's self-documenting, having this block. Of course, extra arguments help, but it's kind of easy to know what is happening just by looking at the blocks and the diagrams. But compare that to having to explain or understand what is happening in the system just by looking at these 2,000 plus lines of code. Good luck with that, trying to understand it. It's very hard. And not only that, it's hard to maintain also, because you have to deal with memory pointers. You don't have to deal with all those issues in Simulink. And it is important to generate C code because C code is much more efficient than Simulink and also integrates better into an embedded environment if you want to put this in an embedded system. So there's a lot of advantage of using generated code. Okay, so this is the entry point. This has the name of the model _step. Okay, but also Simulink recently added this view in which you can see the generic code. You can search in here for the entry point, and let's search for something of the algorithm like the optical flow. Okay, that takes us here, and we have traceability, so we're also going to take you to where it comes from, and this is basically a function. In this case, that function is implemented somewhere else, and if you look for that function in the generic code, you're not going to see the C file for that, but you do see the object file. Last time I checked, I saw it. Maybe not this time. Yeah, this is the one, optical flow HSH. You see the OBJ, but you don't see the C file for it. Okay, but also let's look for another one. Let's say that we want to see the blob analysis. We saw the traceability from here to here. Now I'm gonna see in the other direction. You can see that took me into this code. It's all purple, but it's part of the regular code. Let's just look for blob. It's the same, and then I click here and it takes me to the same place. But notice that this is not a function. There's a bunch of nested for loops, so it's doing the computation to find the bounding boxes somewhere around here. The S function was inline. You can see it's an S function. It was inline into the main code. So somewhere around here, you're gonna see the bounding boxes being created. Yeah. So that's it for the video. And of course, if you want to try the generic code to see if it gives you the correct answer, you can use Seal. There's an app for that, I understand. You can search for it. Let me look for it. Seal Pen Manager. So with this, you can run verification and compare the results. I'm not gonna go through that, but what that is gonna do is gonna compile the generic code and run it within your Simulink model to make sure that it runs and it gives you the same results as normal simulation, to make sure that the generic code is gonna be correctly integrated into your environment. So in this video, I showed how to detect vehicles using the computer vision toolbox from MATLAB within Simulink, and also we're able to generate code and see the advantages of having generic code basically being done for you, rather than you having to have the pain of doing a system like this much more complicated in C++. Thank you very much for watching.